Hello, my name is Rohit Singh NITWAL. I am second year student of Data Science and Artificial Intelligence at IIT Roorkee. Image processing is a complex task, and the tool of linear algebra provides a powerful application that helps in study and manipulation of images. How do computer perceive images? So basically, the computer represents image in form of a matrix. The matrix, each element of the matrix represents the pixel value, and the pixel value stores the data about the color coordinates that are standing at that point. And for our color picture, we represent it by three color channels, red, green, and blue. And the three channels represent a tensor, and a combination of these three colors give us a colorful image like this. After after we transform our image in digital form, now we have to perform certain operations that help in transforming and enhancing the image or to extract some information from the image, for which the tool of linear algebra provides the essential mathematical foundation that will help us in extracting the valuable insights from the images. Digital image processing is an essential pre-processing step for many applications that are some advanced level applications like face recognition, object detection, image compression, and other tasks. We will be discussing many fundamental geometric operations that can be efficiently performed using linear algebra, like rotation, translation, scaling, shearing, vector transformations, PCA, and low rank approximation using SVD, and how they connect to image processing. There are many complex operations also involved in image processing, and it requires combination of mathematical and algorithmic approaches. It includes linear algebra, calculus, statistics, but for now, we will focus on the fundamental parts of linear algebra that will help in image processing or pre-processing steps. We will be discussing about PCA, SVD, convolution, and basic transformations. So these are some basic image processing applications that rely heavily on linear algebra. The first fundamental step in image processing involves the geometric transformation of the given image. So basically, the most fundamental aspect of geometric transformation is linear transformation. So linear transformation is some transformation uh, that has to meet the following three criteria. If we apply the linear transformation to sum of any two vectors in a vector space, then it should be equal to the transformation applied individually to those two vectors. The second is if the vector from a vector space is scaled and then transformation is applied to it, it should be same as transformation applied to the vector in vector space and then scaled by the vector C. The third is the transformation when applied to the zero vector of the vector space results in the same zero vector in that vector space. If these three conditions are satisfied, then we can say that the transformation is linear. So that's the theoretical definition. And later we will move on to see some visuals of these transformations. There are some properties of linear transformation also, like the sequential application of linear transformation is again a linear transformation. If I apply one linear transformation, then another, the result of those all three transformation is also a linear transformation. And the order of transformation matters. For transformation, we represent it by some matrix. Like in matrix multiplication, the order matters. So the transformation order also matters. Applying transformation A, then transformation B is not same as transformation B, then transformation A. Since the transformation is basically a matrix operation, so the transformation applied to a vector in vector space gives the linear combination of the vector, and it gives the transformed coordinates of that vector. So basically, it's a linear combination, and this combination is dependent on these four constants. So we can say that for the transformation from R2 space to R2 space involves use of 4 degrees of freedoms. A linear transformation does not affect the location of zero vector. After applying the transformation, the zero vector is mapped to the same location as it was before. And while applying linear transformation, it ensures that the parallel line remains parallel like it is before. And the linear transformation preserve all the lines that are present in the grid we are applying the transformation onto. And in its application part, we can use the linear transformation for various manipulation of image, like we can rotate image, we can share image in one direction, we can scale image, or we can flip image vertically, horizontally, or through some axis. The second kind of transformation is what we call affine transformations. These affine transformations are not linear, but it can be said to be consist of a linear transformation and a translation operation. So we can see it here. We can apply linear transformation, like we can scale it, these x and y coordinates, and after scaling, we can shift the position of the coordinates so that the zero vector does not align as it was before. Since zero vector is not mapped after transformation, we can say it's not a linear transformation. And that is the basic difference between linear and affine transformation. Affine transformation is basically linear transformation plus the translation operation. If the if the affine transformation involves the translation factor, then it may even change the origin of our whole reference frame. So affine transformation also preserve lines and ratio of line, but they may not preserve the origin, and rest of the other things that are preserved in the linear transformation are also preserved in affine transformations. Only thing is that the origin may change if we are adding some offset to it. Like you can see it here, after translation, we are adding some offset that helps in translating the position of the image from one position to another. So how can we represent these affine transformations as linear transformations? Because when we are dealing with most of our applications, we need to represent our data as some kind of linear transformation. So here comes a little handy tool that is basically we are taking the 2D data to a 3D space and how to represent that data. So here comes the notion of homogeneous coordinates. So if we if I am having a vector in xy plane of x and y, and now I want to represent a affine transformation or a translation operation in that vector. How can we do that? So we can translate, or we can say that we can represent this xy coordinate and take it to this z axis. So basically we are taking that 2D image to z coordinate of one value, and now we can apply shear operation or many such other operations so that the upper part of the cuboid like shape that we are producing through image can be sheared or linearly transformed. So after that, linearly transformed image can be represented in 2D 2D plane by a dimensional eraser matrix. So in this way, affine transformation can be represented as linear transformation. So here it is its matrix representation. So you can multiply this row with this column and this with this. So you can basically see that you will get this linear transformation plus this point, this linear transformation plus this point, and the one part here. In this way, we can represent a translation operation as linear transformation. So here is what we were discussing before. This is x, y coordinate. We are taking this Cartesian coordinate to homogeneous coordinate. We take it to z equals to 1. Our plane is now standing at z equals to 1 part. And now, after we have moved from this part to that part, we can apply a matrix. So what this matrix is doing, it is applying a linear transformation. So we have applied a linear transformation where we are doing some kind of shifting this. So origin is here, and now applying that linear transformation, we are displacing this part from this upper part from here to here. And after that, we have to go back to Cartesian coordinate to get its transformation image. So how to do that? So we can do that by just dividing by the z coordinate through which we have translated our image. So in this case, we have taken our image from the plane that lied on x and y coordinate and z equals to 0 to z equals to 1. So the translated coordinates of x dash and y dash can be divided by z dash. In this case, the z dash is 1. So basically, what the x dash value is there is also the x dash value of image. So in this way, for our 2D image, we can do translation and also represent it as a linear transformation by projecting it into a 3D space like that, and then again taking its representation in 2D form. So for the degree of freedom involved here, we have this value of 1 fixed. So we have 8 other values. So its degree of freedom is 8. Let's go to a website where we can visualize these linear transformations clearly. Let us apply some transformation to this image of a cat. This is the transformation matrix. It is identity matrix. So it represents the image in its natural state. So let us scale this image by a factor of 2. So it will scale up by factor of 2 in the y direction. This is it. And then to make it pretty visible, also let us also scale it in x direction by scaling factor of 2. So here it is, a big cat. Now what we can do more to this image. So we can do some of the some other operation like sharing, and so let us start with sharing. Uh, Let me take some good decent number, 0.030. So by applying this factor, I have shared this image by 0.3 in the x direction. Now take it back to its original state. Now apply this the y direction, 0.5 here. So you can see that all the grids are changing. You can also see how each vectors that are representing the image also change with that. Let us take back our cat image, and now we will do some more transformation to it. Now let us go to our initial state, and then we will do some rotation on our cat. For rotation, we will go by a rotation matrix that will rotate it by 90 degree. So, and this one. So you can see that our cat is flipped by 90 degree. Now let us move on and apply some reflections about the axis to our image. Uh, I will change these values. Wow, it has reduced its dimension. Now, uh, this is the vertical flip. We have changed the direction of our cat. After that, let us apply some horizontal flip to it. So -1 and 1 here. So that's our cat flipped downward vertically. Now let us apply some other operation to it. Take it 1, take it 1, make it 0, make it 0. And that's our cat transform to the x equals to y axis. Now it's time to play with some 3D images. So here is our 3D vector in our 3D grid. Let us enable the 3D grid view. So here we are. Let us reduce the dimension of this vector. I'm making it 0. Okay. I'm making it 0 by making it 0. Okay. Everything is fine. Now let us bring our cat again to the picture. So here is our cat. Now let us apply some affine transformation to that cat. So we'll do that 2 and 3. So after this transformation, we can see that there is our cat. It has gone some flatness to it. Let us clear it out, make it all fine again, and only perform some basic operations to it. So what can we do? Let us scale it so we can see it in a better view. That's our cat, and let our vector be in the 3D space. So along with that cat, we can also measure the direction that our vector will go on. After, so at last, before moving on, let us apply some shear transformation to this cat. So after that, we will move on to the next section. That's it. That's too much shear. Let us reduce it. Make it something like 3. So this is shear transformation to cat. It is tilted in x direction by a factor of 3, although it is scaled also by factor of 1, factor of 2. So that's our original cat, and let us apply shear factor of 2. Now again, let us apply some shear in this direction, that is z direction also. That's it. That's our 3D case. Now let us move on to the next section. The singular value decomposition, or SVD, is a factorization technique where we can decompose a non-square matrix into 3 components that can individually represent what is going to happen with this matrix. Like this is a m cross n matrix represented by A. We can taken into three parts: U, sigma, and V transpose, where the sigma matrix consists the diagonal elements, and these diagonal elements represent the eigenvalues of the matrix A transpose, and the U matrix is made up of the eigenvectors from the matrix A transpose, and V transpose is the transpose of the matrix formed from the A transpose A matrix. So this is the basic decomposition of a non-square matrix into three components. And in this way, we can represent any matrix in this form. And this form helps us in many ways. We will see how it helps us in image processing part, where these the rank of these matrix decide how much data we can compress and how much data we can extract from the image. One of the most common use of the SVD is in domain of image feature extraction using SVD. So basically, from the matrix A, we can approximate this matrix A by its low rank approximation. So this sigma, like we discussed earlier, that this sigma contains its diagonal element contains the eigenvalues of the matrix A transpose. So if we have the matrix in low rank form, then we would have to store less amount of data. In this way, we can compress our image, or we can say that we can extract the only necessary features from the image using SVD. So this is what goes behind low rank approximation. We take some rank of the matrix, or we can say that in its diagonal element are constituting the sigma matrix, and it is not a full rank. If it is an n cross n matrix, the sigma one, then we have less than n diagonal elements, and these less than n diagonal elements in this matrix, when applied to these U and V transpose, which are also in low rank form, helps us to reduce the size of image, or we can say that to extract the features from image using less data at our disposal. So here is the data obtained from the compression process that we have gone through some images. So basic generalization comes from this graph, where you can see that rank versus percentage storage required. So the percentage storage of required depends on the rank. So for example, if we have an image of size 600 by 600, and after applying SVD, we get a sigma that of size 600 by 600. So on its full rank, it can have 600 features, or 600 rank. So it would require that 100% compression for 600 rank. If we get the same features from less rank, then in less percentage of space required, we can approximate the true image or the original image by its low rank representation. Like for this example, the 100% storage required is something near 330, 340 approximately. And if we can represent this image in low rank form of 100 or 200, then we, for example, for this image with 300 value of n, if we can reduce its rank to 200, then the storage requirement drops to approximately 50%. And if the same image taken to 100 rank, then the storage requirement again drops up to nearly 25%. So we have to check a particular amount where we can retain most of the features from the original image and reduce its rank, so that our storage requirement. Let us explore some codes and see visually what we can do with SVD. We will apply the SVD in our images and see what result it can give and see how low rank approximation can lead us to some compressing. We will analyze how much compression is found at what rank. Okay, so let's start it on importing the libraries. So we will be working on this image. Basically, this image is represented as NumPy array or a simple matrix. After that, we are taking its red, blue, and green channel. Here is its red channel values. Now, using the NumPy function of SVD. Now, let us check the shape of the values for our U, U matrix, the S matrix, and the V matrix. So here are the values. Our U matrix has come out to be 667 cross 667 and S. So basically this function only gives us the eigenvalues. So this S is a simple NumPy array of eigenvalues. We would have to convert it into a matrix form. Here we convert it into matrix form. Now it's a matrix of 667, 667, and we have used diagonal function. So all these eigenvalues are now in the diagonal part of it. Similarly, applying SVD to blue channel and green channel. Now let us see some result for a rank 5 of compression. Here it is. We have applied rank 5 compression, and now rank 5 compression on red. Now let us use this function. We will use this function to compress with our desired rank. We have done this process just to represent what we get in matrix form. By this function, we will compress the red channel, we will compress the blue channel, and we will compress the green channel in some intermediate rank. For this example, for this image, we have seen that its full rank is 667. So we will reduce our matrix to rank less than that. So this function will give us modular approach to that. Let us compress that image in 5 rank and see what we get. So at 5 rank, we are getting the image size of 1.25%. So our image is compressed to its 1% size. Now let us see 20%, sorry, 20 rank. At 20 rank, we are getting 5% compression, and the image is some kind of blurry thing. Let us see what we get at 100 compression. Now this image is pretty decent. It is similar to the original image. So let us see some widget and interact with the image to see how we can see that. So this is 48% compression at 194 rank. This is at 250. Now it is looking pretty decent. So we can use this image to represent our original image, and it saves our storage. Almost 40% of storage is saved by this 250 rank approximation. As we move to much more rank, then instead of compressing, it is expanding. You can see that it is 103% of the original. So basically, we have to use low rank approximation. It will be helpful as it will compress our data, and also it will retain some useful information in it. So we have seen that low rank approximation in isolation. Now, let us see it in same frame so that we can compare how it goes on. Here is our second image. Uh, we have applied SVT to it. Now, we will analyze how the storage capacity varies with reducing its rank. So, after this operation, we can check what is the maximum energy that we can optimize it for, and the optimum rank. If we want to reduce its size by 70% or 30% storage, we can go up to optimum rank of 80, and to optimize for energy, we can go to its rank of 174. So at rank of 80, we will get a considerable approximation of our original image. Let us see. So here it is at rank 5, rank 20. So the optimal rank was rank 80, and you can see that at 31.25% of information stored, our rank is 100. It is a good approximation, whereas our original image is this. So we can interchangeably use this for this. And now it's time to see the plots for rank versus log of our sigma, rank versus the information stored, and the rank versus percentage of storage required. These are the plots. So the next application of the linear algebra in image processing is convolution process. Convolution is a fundamental operation in image processing in which we take a small matrix that we call as kernel, and we convolve this kernel through our image matrix. So what is convolution operation? So convolution is basically sliding this kernel matrix through each of the pixel and doing multiplications in such a way that it takes care of its adjacent pixel values and gives some kind of average value that can replace that pixel value at that point. So this is the convolution function. So it is a fundamental operation, and it involves the linear operation. The kernel matrix that we use can be described in many ways, and its description is based on the kind of work that we want that kernel to do. This kernel can be represented as a matrix that can do blurring, that can do sharpening, or that can do edge detection, or many other filters that we can use to convolve this kernel and get our desired result. So here are some basic kernels. This is a blur kernel. The blur kernel takes care of the adjacent pixel value, and it reflects the adjacent values, and it kind of smoothens out the pixel values by its surrounding pixel value. So this is a typical blur kernel, although not every blur kernel is represented in this way. It can be in many forms, and the most commonly used is Gaussian blur that is based on the Gaussian distribution based on the kernel size, which takes the higher weightage of the initial values near the center of the kernel and less weight of outside values of the kernel matrix. And this is another type of kernel, outline kernel, where it can be used to highlight the pixel differences that arise at the boundary points. So this outline kernel is used for edge detection, and this is another kernel, namely emboss kernel. This emboss kernel gives the illusion of depth to the image. You can see that it is a kind of symmetric matrix, and it is represented in such a way that it gives the information about the depth of the image. So now we will see the application of these kernels in us image. So in this image, you can see that it is the original image, and I have applied the following kernels to this image. For example, I applied the embossed kernel that was represented by this, and applying this kernel and convolving through this image gives the depth information about this image, and convolving that image through this outline kernel gives the outline of the image, and this is the blur filter. So you can see that this filter is pretty much weak, as it very less effect on the original image. We can use much more stronger blur filters, but for this picture, we use the filter which is pretty weak. So this is convolution operation in action. You can see that how convolution process goes by. This is the kernel, and it is being applied to that part of matrix, and it is replacing this point by this point. It will go on and stretch through the entire image until all pixel of the image is convolved. And here for this edge detection kernel, we have got a pretty decent edge boundary. These types of kernels are basic part in pre-processing of the images and can be further applied for other computer vision applications or enhancing, or it is widely used in deep learning. So next we have PCA for application to image processing, and PCA is most commonly used technique for dimensionality reduction. It can reduce dimension for many types of data, and so it can be also employed to the image data to reduce its dimension, or in a way to compress the image by reducing the excess information that we have. So we can represent the same image in a less amount of space. PCA is mathematically orthogonal linear transformation. It transforms the given data to a new coordinate system. The new coordinate system is represented by the coordinates of the principal components. Based on the dimension of the data, it can have multiple principal components. For example, in this 2D, two-dimensional data, we can represent this data as we can represent this data by using two principal components. The first component is the major component. The first component, uh, principal component, represent the greatest variance on the data, and the next component that we use, or the second component, represents the second greatest variance in the data. So we will use this PCA to reduce the dimension of our image. If we have multidimensional data, then we can reduce the features of data by transposing the original data to the reduced dimension of the data. In this way, we are reducing essentially the dimension of the data, and by reducing the dimensionality, we can further save some space and make sense of the data. So how to apply the PCA in our data? In a nutshell, PCA obtaining PCA involves some steps, like first we can calculate mean of each feature. For example, let us take this two-dimensional data. We have an x and y axis. For this data, we can find the mean or central tendency of the data. After finding that, we have to find the covariance of the data. Now, for covariance part, we will find the covariance pairwise. For feature 1, we will find its covariance with respect to itself and with respect to other feature. Similarly, for the second feature, we will find its covariance with respect to the other feature and with respect to itself. Based on the amount of dimension that we have, we can found that if we have n amount of features, then our covariance matrix that we form will be of and cross dimension. Finally, as we get the covariance matrix to find which principal component we want to reduce our dimension to, we have to find its eigenvalues. So this covariance matrix we take and we find its eigenvalue, and the greatest eigenvalue corresponds to the principal component or the first principal component along which there is the greatest variation. So after determining the eigenvalues and eigenvectors, finally we get our principal component of the principal component eigenvector, and we can now apply this principal apply this what we can apply our that first principal eigenvector to the data point that we have obtained by normalizing it to central tendency, and this operation gives us the first principal component of our data. In this way we can represent our data in one dimension, and that is based on the first principal component. Here you can see that this 2D data is now represented in first component or the first principal component, and these values can be mapped to the principal component. So this 2D data is now in one-dimensional form. Now let us see our image processing part, where we will use the PCA for image compression. The image we have is of large dimension, about 800 cross 500, and we want to extract its major features while also compressing its size. So in order to get its representation, we can find some principal components and project our data to that. If we use less components, then we get a fuzzy picture where the representation of image is distorted, and after some iteration, if we take more and more principal components, we can get more and more data. By optimizing the principal components numbers, we can get an approximation to the original image. At optimal value, we get a better approximation, and also we will be saving a lot of space, which will compress the image to the desired size, also saving our resources. Now we will see some codes. So let us apply PCA to this image and see how we get its compression. So this is our image. We will apply PCA to it. Let us take that image. Oh, we have C-mapped this image to grayscale, or we want to just take the matrix form of the image. So we have taken out the channels out from the image, and basically we have taken its grayscale representation, pixel value ranging between 0 and 255. Now, using sklearn, we apply the PCA upon it. So we want to take the principal component. We are analyzing what principal component will give us 95% of the variation. So it is a table. So if we take about 50, about greater than 50, then we can get 95, above than 95% of variance. Okay, this is 46. At 46 principal components, we can get the variance of 95%. So we will get pretty decent approximation of the original image after these 46 components. Let us now apply that. So first we make a function, to construct and plot image with given number of components. Now let us apply this image. For this image, we have taken k equals to 150 components. Now let us take some varying number of components. We have taken 10, 25, 50, 100, 150, 250. Let us set some more values, 300, 350, 400, and see what's the result. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 9. Let's change the subplots. So these are the images with 10 components, 25 components, 50 components, 100 components, 150 components, and 250 components. These are the approximation that we get, and you can see it from the image that 150 or 100 is pretty good, and this looks very nice. About 50 is not a decent, it kind of blurry image. So in this way, by uh, taking more and more components, we can approximate to the original image and also save some space by compressing the size of image. So far, we have discussed some of the basic applications of linear algebra in the image processing. And as the image processing is a vast field, and only using linear algebra will not be sufficient for the full-fledged application to the image processing. And we might require other tools, other algorithms, hardwares, softwares, and other parts of the mathematics to deal with the images much better. And essentially, whatever we have discussed can serve as the intermediate part or the image pre-processing part of the entire image processing, which is a pretty complex task. And for much advanced image processing, we have these super resolution. We have to increase the resolution of the image. We can 3D, we can do 3D reconstruction of the image in painting. For example, we have some corrupted image with missing parts of it. To reconstruct that image, we have to use the image processing in deep learning based operations. We have GANs and CNNs to do such image processing. And whatever we have discussed till now, like that SVD and PCA for image compression, these can be handy, but for most advanced compressions, we have pretty much developed algorithms like JPEG format. Uh, we also need image processing in object recognition and tracking, which are various application in robotics and other applications for images. We can have many applications, and one such example is this use of CNN. CNN is a deep learning based computer vision technique, or CNN stands for convolutional neural network, where the basic operation of convolution is used in the pre-processing or in intermediate parts. And the CNN operation, the CNN architecture is used to process image more efficiently. It utilizes the concept of machine learning neural networks to process the image. So this is one of the most widely used algorithms, or we can say the best algorithm that we use for automated processing of images. CNNs are widely used for detecting pattern, but for these, we also need the basic application of the linear algebra so that we can understand what's going behind CNN and more advanced features of image processing. So here is some data from a research paper where you can see that various image processing techniques are used to get filter out the images. We have many images of this paper and this butterfly. We have used various techniques. This is the original image, and we have upscaled the image with factor of 3, and we want to see which representation gives better performance. And this is SVD, and you can see the best outcome is given by the CNN, super resolution CNN. Although for most of the times we might be using the advanced algorithms to do the job of image processing, but to get to make a little amount of improvement or to boost the performance of our image processing tasks, we have to use those basic image pre-processing. For example, in medical or biomedical application, we have to diagnose a particular disease by the visuals of some some area of the disease. So in that case, we have to use various image pre-processing techniques. We have to use those image filters. We have to use, we have to combine the images. We have to set the thresholding. We have to blur the images. We have to extract the features. And in that time, we have to make those leap of improvement. And to make that leap of improvement, we need a boost in performance even by 2%, 3%. And that is also a considerable improvement for the case of biomedical application because each degree of accuracy is very crucial for diagnosis of a particular disease. That's it, and thank you.